So welcome everybody to this new imaging seminar. Today we are pleased to welcome Laurent Seppecher from École Centrale de Lyon. Laurent is a maître de conférence at École Centrale and is also affiliated to the Institut Camille Jordan in Lyon. Laurent obtained his PhD in 2014 from the University Pierre et Marie Curie in Paris, where he worked under the supervision of Habiba Marie and Laurent and Jocelyn Garnier. And then he spent a year at MIT, where he worked on inverse problems in seismology in the group of Laurent Desmanet. Laurent's research focuses on inverse problems in what is called multi-physics problems, where actually one can use internal data to reconstruct whatever parameters of interest. And this is a particularly new area in inverse problems, and Laurent is interested in those things in the context of seismic and medical imaging. And so today he will talk to us about stability and discretization techniques for this form of elliptic inverse problems with internal data in elastography, and in particular with application to breast tumor, detection of breast tumors. So Laurent, the floor is yours. Thank you again for accepting our invitation. And, we're looking forward to your talk.
Thank you. Thank you very much. And thank you very much to everyone for being here. It's a real pleasure to talk a little bit about what we are doing. It's been a while that we haven't seen each other. And so I guess that next time would be like seeing each other at some conference and meeting. But so far it's still very nice to see you online and give this little presentation, this little talk about what we're doing right now. And so the topic of today is about mostly elastography, but could be a little bit more. I will try to describe the problems we are dealing with in some kind of general manner, which is finding some elliptic parameters, so elliptic coefficient in elliptic PDEs, when you know some internal data, some solution of the PDE inside, and it has a great application in elastography, in medical elastography, but also other kind of elastography, but 90% of the interest about elastography is in medical imaging. And I will like somehow show you the mathematical question behind this problem, which has been studied a lot already, but there are still some very interesting questions going on with this topic actually. And so I try to show you like half the applications. We try to be very useful, very applied somehow, try to do some real medical imaging. And in the other side, we try also to do some nice mathematics and understand the problems, the operators we are dealing with, and try to somehow generalize a little bit. So do not hesitate if there is something which is not clear during the talk, just ask me and I can like somehow give more explanations. And so I will start by an equation here, which we call the reduced elastography problem. Okay, and the topic is to find a parameter mu in this main equation here. In this equation, mu is a scalar function, and S would be a matrix function. Okay, most of the time symmetric, because it could be a strain tensor, for instance, and F is a vector field. So it's a vectorial equation. The divergence of mu S is a matrix. And we'll see that like several problems can be reduced to this quite simple equation. And the problem is to find mu. Okay. The parameters of this problem are, what we know about this problem is the following. We know Lipschitz domain, which is not of great importance, actually. It could be a subdomain of something, some subdomain of interest. And inside this domain, we know the tensor S. So S is a matrix. We assume it's a bounded matrix, okay? Not necessarily symmetric, but we know it. We can deduce it from the data. We'll see how. And F is also something that we know. It's a given vector field, okay? Note that F could be 0 in some cases. If you think of we'll see it later, but the elasto-static problem would be with a F equals 0, for instance, in some cases. Or in some conductivity problems also, you can have F equals 0. And when you have F equals 0, the question of finding mu is somehow finding the null space of some kind of differential operator, okay? So mu is the unknown, is a parameter function, which is a scalar function, okay? We just try to find one function here. So before going into the math, let's talk about a little bit about the context. So this is the outlines of the talk of today. So I will go back a little bit to elastography to like refocus on what we know about elastography, what exists about elastography, and something that it works quite well actually. And then I will try to describe our approach, which is like somehow a straightforward discretization of what we call the reverse weak formulation of the equation. And this involves actually the introduction of the Inf-sup constant or LBB condition. I will explain it later, which is very similar to Stokes problem. When you try to look at the stability of the Stokes problem and the stability of the discretization of the Stokes problem, you will show some constants called Inf-sup constant or LBB constants and Inf-sup condition, LBB condition, which will give you the key for the stability of what you are doing. Then after this definition, we can like deduce some stability estimates, okay? And after this theoretical part, we go back a little bit to practical, and I will show you a quite nice finite elements technique, which is very well suited for the inverse parameter problem, okay? Which is not great for the forward problem at all, but is really good for the inverse problem. And we'll see that it's nice to build, I mean, to consider different finite element, different discretization when you go to the inverse problem instead of the forward problem. Then I will show you some numerical and experimental illustrations of this. So it's a work in collaboration with Élie Bretin from INSA de Lyon and Pierre Millien, which is at Institut Langevin in Paris. And also it's based on previous work with Habiba Mari and some other colleagues in the physics. I will cite them later. And so the basic problem of elastography from internal data, which is important to specify, is the following. You have an elastic object which somehow satisfy the linear elasticity equation, and you move it, you apply force, you apply some displacement at the boundary, and you record the displacement field inside the domain. Okay, so you somehow make an experiment that solves the linear elastic equation. You record this displacement field, and from this displacement field, you want to deduce the elastic properties of this medium. So it's very easy to explain this problem. The goal is to measure the elastic parameters. Okay, and for the medical elastography, we are interested in soft biological tissues. Why? Because we have for the elastic parameters, and specifically for the shear modulus, we have very high contrast between different tissues, between fat, between muscles, between blood, between tumors, which is really important. And it shows to be a very good discrimination parameter between pathological states. For example, we can differentiate malignant tumors to non-dangerous benign tumors using this shear modulus value. Okay, so it's a very important criteria. The problem is that it's not easy to image. Actually, it's not easy to reconstruct because there is a high contrast. It was an advantage here. It's a difficulty because high contrast creates some very complicated waves inside the body, like a lot of scattering with not plane front waves. And so you cannot use classic math as a time reversal or a technique like this to make imaging using the elastic wave, the shear wave. Okay. And also you have difficulties to have a small wavelengths. You know that wavelengths is the key for the resolution. Small wavelengths give you a very high resolution. And here, with the elastic waves, you're not able to have a very small wavelengths, and so you cannot have resolution using waves and scattering of waves. So it's a very big difficulty. So to stay with the context, this is an image of the X-ray of a breast tumor. Okay, and you don't know here if it's malignant or only a pre-tumoral tissue, which is not harmful. So the X-rays show you an image, but it's not able to give you a good discrimination. Okay, the other problem is that it's harmful. Like you have a X-rays, so it's irradiating the tissues, so you don't want to use them very often. So it's not so easy to choose to use them or not, specifically for a young woman who wants to have breast cancer detection, breast cancer prevention. In the other hand, the ultrasound, sorry, there's an L missing, the ultrasound imaging phase, because the contrast is not good enough. Okay, so the image you will get is too poor in the tumoral tissue to detect it, or at least to have something like to have a discrimination. So it's not you don't have enough contrast actually. But the shear modulus is very high. So let's like focus on imaging this. So what are the kind of data you record when you image a tissue and you displace it? This is this kind of data. It's a movie where you see the speckle of the tissue moving a little bit. So you see that the movement is not important. And actually, you don't see any hard or soft tissue inside, just see like random speckle moving a little bit. Okay, so this is really the root of the data, the starting data you want to deal with. Okay, so the first step would be from this image to detect the displacement field. We call it step 1. It's not of interest today. We'll more focus on step 2, which is to recover the shear modulus and the elastic parameters from the displacement. And what you want to reconstruct is something like this. From this video, you want to show this image actually. So on the left side, you see the ultrasound image. So you don't see really much the contrast, but you see that there is something. And you want to produce the right image where you have a value of the shear modulus. Okay. And you can distinguish here that there are 2 different values of the 2 inclusions. So it's not a real tumor here, it's a phantom, it's like a laboratory experiment in soft gel phantoms. And you see that this is something that you want to recover because it will tell you this is a dangerous tumor, this is not a dangerous tumor. Okay, so this is the image we want to construct. There are another technique which is based on wavefront, and you send some shear waves. Okay, and what you want to do is also to find the shear modulus, but this time you will use the speed of these shear waves. So it's kind of secondary way to find the shear modulus. Okay, and actually this is working quite well. Actually, you can see here on the left that it's going faster. There's kind of a bump, which means that the shear modulus is higher. Okay, and from that you can deduce somehow the value of the shear modulus. Some people do that, and for example, this is an image you can get from this technique. This is a real image of thyroid nodule. Okay, and you see the difference between a soft one on the left and a hard one on the right. And you see that you can distinguish the shear modulus using this speed of wavefront, which is very interesting. And so to summarize the general idea of elastography, you somehow you give a perturbation, a mechanical perturbation of the media. You track the response of this mechanical perturbation inside the media, and you deduce the reaction of this medium, and you try to deduce the elastic properties. And there exist like few ways of doing this imaging. There are the MRI elastography. In MRI, you have enough frame, you have enough speed to track some elastic displacements. So it works with MRI, and you put some mechanical perturbation and you record them in MRI, and you can do elastography. You have ultrasound elastography. We'll mostly focus on that. Okay, you just record it with an ultrasound probe. And there are also developing technique for the OCT, optical coherence tomography elastography, which is that you will use some kind of laser beam to scan a little object, a little piece of biological tissues. It's more like for biopsy elastography. You will want to see inside a little piece of the tissue. And the OCT is a technique to image a slice of this little piece of tissue with very high resolution and very high speed. So you can see a lot of displacements using OCT. Okay, and you can have several kinds of perturbations applied, some static or quasi-static, just move and use the static elastic equation. You can do dynamics, so sending waves, like pulse waves, or harmonic, okay, so harmonic waves. And the dynamic will bring you some good images so far. The static, not so much, and we are working on that. And the harmonic is also working. Okay. So just to clear the first step, then we go to the second one. The first step is mainly made by speckle correlation. Okay, you have several images. You have a movie of a speckle. You see the speckle moving inside, and you have some technique of pattern correlation, which deduce the displacement vector field from a series of images. Okay, well, this works quite well. There is another technique which is based on the optimal transport. Okay, so you try to minimize a displacement between an image at t plus dt and image at t, and you can find the displacement field like this, but it will need some regularization term here. Okay. So this is called the optical flow method, but it's a whole domain of research and it's not of interest today. Okay, but you can think that this first step is well done. Okay, we have access now to very accurate displacement field. Okay, so the people working, physicists working on the laboratories can give us directly some very good displacement field actually. And the real challenge for the mathematician is to do the second step, to deduce the parameters from the displacements. Okay, so once you have the displacements, you go back to the main equation, the main physical equation here, which is the linear elasticity. Okay, so it's one model. You can have other models using viscoelastic equations, but somehow the idea behind that is the same. So you can like try to do everything with linear elasticity and then go to more complicated stuff. Okay, so you assume that inside your biological tissue, the governing equation is this one. Okay, so you have like linear elasticity. You don't have complicated tensor, you just have like the two Lamé coefficients, okay? And so you have lambda and mu. Mu is the shear modulus, lambda is the compressive modulus. And you have some boundary condition that you apply to create some displacement, okay? E of u is the strain tensor, so the symmetric gradient of the displacement here. Lambda and mu are the two Lamé coefficients. And you want to recover somehow lambda and mu together. It's always two coefficients when you deal with linear elasticity. You can somehow simplify a little bit. The first way of simplifying this equation is to assume that lambda is known. It's not too big assumption in when you are looking for soft tissues imaging, because the contrast on lambda is not too great. So lambda is very high, okay, but the contrast on lambda is not too big. It's about 10% max. And so you can somehow do this assumption without perturbing too much the imaging of mu. Mu, the contrast is like, you can have like 10 or 20 times increase of the value of mu if you are inside the tumor, for instance. So the contrast is much higher on mu than on lambda. Okay. So if lambda is known, then you can take the second term, the term in gradient lambda divergence of u, you can put it with the f, saying that you know it, okay, and you just want to find mu. Okay, so a lot of work have been done on this particular equation that we call the reduced elastic problem here. So we can cite G and McLaughlin, for instance, but also Guillaume Ball, Bellis, Imperial, and Monard, who proved some stability and some technique to reconstruct mu from this equation here. And the main idea behind these mathematical studies are that this is an order 1 PDE, linear PDE, that you can see as a transport equation. And so you can try to solve this transport equation using a characteristic flow, for instance. And so I just give you a few lines to explain you how they done this thing. You just split your equation here, which is divergence of mu strain of u, okay, in two terms. Okay, so you have the symmetric gradient of u, which is a matrix, the gradient of mu, which is a vector field, plus mu times the divergence of the strain here. And then if you assume that this strain is invertible everywhere, and this is the hypothesis that everyone does for this equation, you can multiply by the inverse here, and you end up to something which is quite simple. At the end of the day, you have something like gradient of mu plus mu b equal f, okay, where b is given, f is given, and you want to solve this problem. So it's a vectorial problem of order 1, and techniques using transportation of the characteristic flow from the boundary, let's say, will work. Okay, and you can prove uniqueness, for instance, using this technique. The two problems of this approach is that you need several measurements to do the proof, okay, and we think that one measurement would be enough in this equation to find the shear modulus. And also you need strong smoothness hypothesis on the data. You also need boundary data. And actually in practice, it's not easy to get this smoothness hypothesis because you have like discontinuous shear modulus. You also don't know very well the boundary data. It's extremely hard to evaluate the boundary data because when you push on the body, when the physicist push on the phantom, it's really hard to evaluate how much it pushes, how much is the force. Okay, so the boundary condition is not known precisely. So it's a very powerful theoretical study, but it still has some problems to be applicable. This is another technique which works actually also, but has some disadvantages, which is a most known technique as simply the least square or a kind of minimization technique, where you want to minimize a forward problem, which takes the shear modulus mu and gives you the displacement field u of mu. So to define this map, you have to know, of course, F, which could be a dTtu in case of dynamic data, of course. And you have to know also the boundary force you apply. So if you know all these quantities, then you know the map capital F. Okay, and then you can try a minimization, like a least squares type of technique, where you minimize F of mu minus your data, plus some regularization. Okay. So it works also, but have some very major issue. The first problem is quite slow, because the problem is known to be flat somehow. You don't have a good convexity of this map F in the neighborhood of the solution. So it's a big computation problem, actually, to do something efficient here. And also, like before, you need a good knowledge of G, and you need the knowledge of mu at the boundary, which is something actually you don't know, and it's very hard to evaluate. There are some techniques with some virtual subdomain, where you try to seeing the displacement, you try to deduce the boundary condition, and you will apply this virtual boundary condition to your problem. So it works, but you will have a kind of a very diluted image of mu, and especially when mu discontinuous, you won't see very well the discontinuity. You will have a very blurred version of the shear modulus. And the technique works actually is very strange for me, but still is very powerful. Is that doing something quite physical, saying that we somehow could assume that mu is piecewise constant, and then you can put out mu from the divergence. Okay, and so the shear wave equation looks like this. You have dTtu minus mu times the symmetric Laplacian of u here. Okay, and you can do something quite easy. If you record the displacement field, and mu is like this is actually a diagonal linear problem. You can simply deduce mu as the speed, actually, as the square of the speed of a wavefront. Okay, but this simple idea actually brings the first images of the shear modulus using shear wave. Okay, of course, there are some mathematical problems, because you want to image a non-constant and discontinuous map mu, and you use an equation which is only true when mu is constant. Okay, so there is this this mathematical issue that we cannot accept like this without going deeper in this in this idea. And a last algorithm, which is more or less the same as the previous one, but you don't need perfect wavefront, is also a very simple trick. Using the same technique, you put out mu out of the divergence, which is wrong, actually, which is not true, but it's true almost everywhere if it's piecewise constant. But the almost everywhere will kill, somehow kill the mathematical aspect of this technique. And you can write the equation like mu Laplace of u is equal to rho dTtu, and so you can approach mu like the ratio between dTtu, okay, and the Laplace of u. And it also gives quite interesting images of the shear modulus, this technique. You have some papers here about this technique from Michael Tanter and Matthias Fink and some other collaborators. And also we can cite here a paper of Barbon and Oberai, which somehow gives some mathematical models, mathematical justification of this kind of inversion here. Okay. So this is what exists so far. Like the 4 techniques, and the 2 last techniques works in practice, and some medical device in hospitals actually who produce elastographic image are working on this equation here. So okay, it works, but there are a lot of challenges about elastography. That's why we work on that. The first one is to increase the resolution. because when you see the wavefront and you track the wavefront, you will have a map of mu, which has a very poor resolution, actually, about centimeters, actually. And if you want to image a very small tumor, a very, very small tissue, then you will need more resolution, actually. Another challenge is to be more quantitative. Okay, we want a real value of mu, okay, in Pascal, actually, it's a pressure. It's a big challenge because so far nobody can give you a very precise quantitative value of the shear modulus. Give you images, contrast, but not quantitative values. Okay. Another challenge is to be more stable, like to have the same value for each tries of your imaging technique. Okay, and the existing imaging devices suffers of a poor stability. Okay, it depends on the condition of the patient, if he's moving or not, or if from a day to another, the value will change a lot. So it's a problem. And also we need to be more practical because it's a complex methodology. You have to create a shear wave. You have to record the shear wave with something which is called an ultra-fast ultrasound, or MRI, which is a complicated device. Okay. And so the question behind that is, can we be more practical? Can we do some elastography only with an acoustic probe, okay, or something simple like that? And so with my colleague, we went back to this basic equation here, the reduced elastographic problem, and we assumed that the problem was posed like this, and it's true in many cases. So we were quite happy about this form of equation, because if lambda is known, as we said before, you take S is twice the strain, and so you have this equation. Also, if the Poisson ratio is known, okay, you can build the S with the linear mix of the strain and divergence times identity. You will get the same equation here. Also, when we do what we call the 2D, 3D approximation or slice 2D model, when you press in a 2D slice a 3D body, then you have an approximation, the plane stress approximation, which leads you to a 2D reduced elastography problem. Okay, you can go back to this if you have questions about that. And also it works on other situations. If you want to recover the conductivity, for instance, and you have two internal data, then you can write the two conductivity equations like a vectorial PD, like this, doing the matrix tensor here using grad U1 and grad U2, the two data. Okay, and takes the same shape of equation here, and also other problems. We can see some this equation arising from in finance for the Black-Scholes model. When you want to recover the volatility, somehow you can go back to this problem with some transforms, little tricks. So it's quite general and quite interesting to focus on this equation. So I've been a bit long on my introduction, but don't worry, there are a lot of images, and so the rest would be more practical. So the core idea is the reverse weak formulation. Okay, we don't know actually we don't know the boundary condition, so we only know this PDE. Okay, and so we define the operator of order 1, which takes mu and gives you minus divergence of mu s. And the good way to define it, actually, if you don't want to put some high smoothness hypothesis, is to define it with the variational formulation here, multiplying the equation by a test function in H10, okay, to have only kind of a bilinear form, A of mu V. So you see why we call it reverse weak formulation is because the bilinear form here is in mu and V instead of being in U and V as usual, okay? And you want to solve A of mu V is equal to F, sometimes, F times V. And this weak formulation, we call it the reverse weak formulation, okay? And so the problem is find mu in L2, okay, such that A of mu V is equal to FV for any test function. So it's a good point of view because it cancels all the boundary information. You don't have it, so it doesn't appear in the problem. Okay, and that's why we use h10, function h10. So this is the only thing you know. So the question is, can we solve this problem, and can we approach this problem by discrete problem with stability? Okay, no boundary data is used, and only smoothness hypothesis we take is S is bounded, which is a little smoothness hypothesis actually, but very not restrictive. Okay, so let's try to see what we can say on this problem. And it's quite easy to discretize with Galerkin because it's a variational formulation. So you can use Galerkin approach to give a discrete version of this reverse weak formulation, as you do for the classic weak formulation. Okay, so let's try to give a numerical approximation of this problem. So we approach the spaces by finite dimension spaces. So MH will approach L2, VH will approach H10, like we usually do in Galerkin method. And we have a new problem, like TH mu H VH is equal to FH times VH. Okay. Okay, so MH and VH are two spaces, and it's very important to choose them well, that will approach the two spaces L2 and H10. TH, it's an operator, will approach T in some sense, and VFH, the right-hand side, will be approaching F. Okay. So let's fix what we mean by approaching spaces. First, it's quite simple, but let's fix it. So MH will approach the Hilbert space M if for any point of M you would be approached by a sequence of element of MH. Okay. In other terms, you can define the orthogonal projection from M to MH. Just imagine the piecewise constant approximation of a function here. And you will say that MH approached well when the limit, when H goes to 0 of PH mu minus mu is 0. Okay, so it's a punctual definition. It's not a uniform over M. Okay, and so we define what we call the error of interpolation, which is just the relative error between the projection of mu and mu itself. Okay, so it's very basic, very classic. So everyone works like this when you do Galerkin. For the operator, is the same, actually. You will discretize it, but there is a little difference with the classic discretization of the operator, is that you have some data inside. You have the S, and the S depends on your measurements. And so when you approach T by some operator TH, will go from MH to VH prime here, so the approximation of L2 and H minus 1. You will have the same formulation, of course, but instead of F, you have SH, which is just an approximation version of S. And so the first question is that, okay, when you define this, what is the good norm to measure the difference between TH and T? Okay, is the good space is like the linear operators from L2 to H minus 1? It's not clear, actually. So let's do the difference, just to fix this once. You have TH minus T, the error you will do on the operator, apply to mu and the test function V. And you can bound this quantity here by the infinite norm of mu, the norm SH minus S in L2, okay, and the norm of the test function. And this is important. You want to use L2 for SH minus S because you want to somehow to control the noise, and you will control the noise in L2, but you won't control the noise in L infinity here. Okay, so you choose L2 in SH minus S, so you have to put L infinity on mu. Okay, and this is a little problem actually, because when you do so, the error you do on TH minus T is small in the topology of the linear map from L infinity to VH prime. And this topology is actually weaker than the topology of the linear map from L2 to VH prime. Okay, so you have an approximation which is weaker than the space where TH and TH are defined, actually. Okay, and that will cause a little problem, but actually things works also. Okay, so you have this approximation. And so we give a general definition of the error of interpolation of the operator between t and th as the norm of th minus t for the spaces L infinity and VH prime. Okay, so you can write it like a double sup like this. Okay, this is because of the practical situation that you want to use this norm and not the other one, which is wrong actually in practice. Okay, you can see that this error will contain both the data noise. If you have noise on the displacement, you will have noise on the strain on S, and you also have the error of the interpolation over MH and VH, of course. Okay, so these two errors are contained in this term epsilon op, the error on the operator. Okay, and actually, the fact that you don't have the classic norm, you have this different topology for the error, you cannot use directly what we call the sensitivity analysis of the Moore-Penrose inverse. Okay, there are a lot of literature about how to inverse an operator which has some uncertainties. Okay, how the singular values moves, how can you invert the operator with noise actually. And so there are a bunch of results that can do this. And actually, most of them will use the fact that th minus t is small in the good space. Here and in here, it's not small in the good space, so you cannot use directly this analysis of Moore-Penrose, which is very well known. But you can like follow the idea and try to adapt to this particular situation. Okay, and so yeah, there is this literature about how to inverse th when you know that t is close to th and when you know that t is a closed range operator. Okay, so this is the error on the right hand side. It's just the error, the relative error on f. So there is nothing important here. Okay, the difference between fh minus f. Okay, so the question are: is the continuous problem invertible with stability? That's a big question. Is the discrete problem also invertible with stability? Okay. And the last question is the solution MH of the discretized problem, is it close to mu, the solution of the continuous problem? So there's three big questions that we are interested in. So let's go to the Inf-sup constant and the Inf-sup condition. It's really important here to see that the case S equal identity everywhere is very simple because it gives you an operator T mu, which is exactly the Nabla operator, gradient operator. Okay, T mu is minus gradient when S equal identity. So at least how can we invert the gradient operator, and can we adapt this to any matrix S? So we know a lot about that. We know, for instance, that it's a closed range operator, which means that you can invert it with stability. Okay, so if omega is Lipschitz, then the inverse is stable on the orthogonal of the null space. Okay, and equivalently, you can say that the Nabla operator, the divergence operator, satisfies what we call the Inf-sup condition. It's the same actually. If you look at the Inf-sup constant, which is defined here, you do the sup over all the test function v, and you take the infimum over all the function in the orthogonal of the null space. Okay, this value is called the Inf-sup constant, and if it's positive, we call it the Inf-sup condition. Okay, and you see that C is just the inverse of beta here. Okay, and so this is the good criteria to inverse the gradient, of course, in the orthogonal of the null space. So we want to do the same, of course, with our operator. But even for the gradients, there is a danger. If you don't choose the interpolant spaces MH and VH well, then you have a discrete Inf-sup constant, beta H, which is taken over MH and VH, which is not as good as the beta, actually. So it can decrease to 0, it can be 0, if you don't choose well the spaces. Okay, and this is a big issue. And people who are dealing with the Stokes problem knows about that. And they are looking for a pair of finite element spaces that satisfy the discrete Inf-sup condition. Okay, they call it Inf-sup stable elements. This plays an important role in like Galerkin approximation for the Stokes. And somehow it's also the key problem for our inverse problem. So for the theoretical study, we already proved something last year with Habib, Amari, Elie Breton, and Pierre Millien, is that the continuous operator, in some good cases, is have a nice null space, and also it has closed range. Okay, so if S is smooth enough, like W1P, and if the is invertible everywhere with this kind of hypothesis, the determinant is greater than a constant, then you can show that the null space is at most of dimension 1, which is great, and it has closed range. Okay, so it's like a gradient. It works like a gradient at worst. Okay. Okay, it works also for piecewise. You can extend a little bit to piecewise, but it's hard to do. Okay, and you have a minimal assumption on S, and the question of what is the good assumption on S for that operator to be a closed range operator is so far unknown. Actually, we don't know we don't know any math about that. Okay, and we'll be very interested on this this question. Okay. Do we need smoothness? Do we need piecewise smoothness? We don't know. Is the determinant of S positive something that we need to prove this? Actually, the minimal assumption is not known. It's an open question to us. Okay, so let's give a few definitions about this operator. Alpha is the infimum over all the space. Okay, the first Inf-sup. So it's just actually the first singular value of T. Okay, and rho is the norm of the operator, so somehow it's the last singular value. Okay, it's very classic. And so how to define beta? The second singular value, actually, if you take T equal gradient, alpha equals 0, okay, is the first value. The second one, it's a little bit more complicated to define it, because if you don't have a null space, it's hard to take the orthogonal direction of the null space. And a way to avoid this problem is simply doing this. You define beta E, okay, in the direction E, of the infimum over the orthogonal of E, okay, for any direction E. And then you define beta as the supremum over all the direction E. So you take all the hyperplanes, actually. It defines a beta, and actually this beta is the same as before in the case where you have a null space. Okay, so it's a good way to define the second, if you want, the second singular value of your operator, even if the operator is a little bit complicated. Okay, so the beta, okay, so this is just to show that it's the same if you have a null space. If you have a null space, beta of T is beta Z of T, where Z is the direction of the null space. So you are orthogonal to the null space. And for the gradient, it's the same definition. So it extends the classic definition. And even if you don't have a null space, if you have a minimizing direction, like a direction Z such that T of Z equal alpha, the first singular value, then beta would be built taking the infimum over the orthogonal of Z. Okay, and so you will like follow this exactly the same idea as the Inf-sup constant for the gradient. Okay, and this is always true for finite dimensional and finite rank operators, so you're good with this. Okay. So when you take the discrete version of it, there is no difference. So the discrete version of beta is that you take the infimum over MH instead of L2, and the supremum over VH instead of H10. Okay, and the same problem occurs that beta can be worse. Beta of TH can be worse than beta of T. Okay. Okay, and so you have to somehow know the behavior of beta of TH. And the only result you can prove here is what we call the upper semi-continuity of the Inf-sup constant, which is well known for the gradient. And it also works for TH, okay, for T and TH. And so the results only says that the limit sup of alpha de TH when H goes to 0 is smaller than alpha de T, and the same for beta, okay, under minimal assumption that you have a null space and the solution of TZ equals 0 is bounded. Under this assumption, it works. And that says that beta of TH is always worse, actually, asymptotically, than beta of T. You cannot hope that your discretization will bring you a better stability at the limit than the continuous stability constant. Okay. Okay, and you can use it to show that T has closed range, actually. Okay, if you see you show that this is bounded by below, then beta of T is also bounded by below, and so you show that an operator is closed range. So it's quite interesting, an interesting result. Okay, two stability estimates, and I'll show you some pictures. So the two stability estimates works like this. So don't worry if it's a bit large. The only thing you have to see is that when you want to solve TZ equals 0, you will solve THZH equal alpha. So you minimize the quantity THZH, okay? And you have this result which guarantee that the ZH, the solution of this discrete problem, is really close to the projection of Z. Okay, the projection of Z is the best guess you can have in the finite dimension space. Okay, and the constant, as we can expect, is in 1 over beta of TH. So you see the importance of this discrete Inf-sup constant, which appears here in the control. Then you have the error over the operator, and you have the error of interpolation of your solution, which is normal terms. Okay. And so you can also say that if beta of TH is bounded by below, then you have a convergence. When H goes to 0, dead H goes to Z. Okay. So it shows you that beta of TH is the key element for stability here. So this is for the case F equals 0. There's the same theorem for the case F is not equal 0. I won't explain it, but it's exactly the same question. Okay, but you have a F in the middle. So don't worry about this one, it's the same actually. I want to go straight to the numericals because time flies. And maybe I will skip this because it's really late. This is a particular finite element space we used. I will show you the numericals directly. So the numericals actually illustrate well the theorem. So we first did the numericals with T equal the nabla operator, gradient operator. In this case, we have the theorem saying that we have stability if beta de TH is not close to 0. So the first thing we do here is to plot to measure beta of TH. Okay, which is great with this theorem is that on the right side, everything is measurable somehow. You can compute beta of TH and you can estimate the errors on F and the error of interpolation. So you can have a quantitative value of the error you do here. And so when you plot beta of TH with different pairs of finite element spaces, you see some nice behavior. Beta of the dashed line here is the continuous beta, the continuous Inf-sup constant. And you see that you have some pairs who are a little bit above the continuous one, for example, for the P0, P2 or the P2, P4 pair, but it will converge below it. We know it by theorem. Okay, and you also have some nice behavior of P1, P2 pair, of the P3, P4, actually. Okay, but you also see some very bad behavior. The P1, P1 pair goes quite fast to 0. So you won't have a numerical stability here. And also the P0, P1, the most common pair of finite element is directly to 0. So it's very bad to use it. So when you choose your discretization, you have to look at this graph and take the one which have a very good beta. Okay, and so you can inverse the gradient with huge stability, directly taking the inversion of the discrete TH. Okay, and you will see that it works and it has a very good stability to noise. Here is a different level of noise. Here. Okay, I don't go in details, but this is just to show you that it's stable. Okay. It's much more interesting in quasi-static elastography. So you have this map of the shear modulus. You press it with forces at the top. You have U1 and U2, the displacement field. And so you build a new operator TH, okay, with this displacement field inside the operator. Then you compute alpha and beta. So alpha has to go to 0 because you are looking for a solution of T mu equals 0. So you are looking for the null space of your operator. So you hope that the first eigenvalue, the first singular value, goes to 0 because the first singular value of T is 0. Alpha of TH converges to 0. Beta of TH does not converge to 0. Okay, and you can see that for different pairs of spaces, you have very bad behavior. So the P1 pair here will decrease strongly alpha and beta. Okay. And the ratio between alpha and beta is also important. You want this to keep small, actually, to have a good estimate. Okay, then the algorithm is very simple. You take the matrix version of TH, and you take the singular values. So you just have to pay attention of your basis. You have the two bases, the basis of MH and the basis of VH. And so the matrix you build, use this basis matrix before and after the operator. But once you fix that, then alpha of TH is just the smallest singular value. Beta of TH is the second smallest singular value. And your solution, the mu that you are looking for, is the first singular vector. Okay, so the only thing you have to do is take the matrix and give some numerical algebraic method for the first singular vector, like SVD type of method, and you will get your solution of the shear modulus. So let's try with this finite element pair, which use hexagonal approximation, and you'll see that it converges when H goes to 0. It's quite strong. Okay. There is no noise here, but you have like real numerical data. Okay, this is for the pairs. I don't go through this. And this is what it goes when you do practical tests with some phantoms. So it works well. And last image using in vivo data. So this is on a breast tumor. It's been made in the beginning of the year, and you apply this method and you have a very fine image of the shear modulus, which is totally invisible in the acoustic image on the left. You really see something on the right side. So I'm really sorry because I'm a bit late, but I will stop here and will thank you everyone for your attention. I think, Eric, we don't hear you.
All right, thanks. My mic was off. Thank you, Laurent, for your talk. It was very interesting. We may have time for a few questions, although we're close to the hour. So if you want to ask a question, please use the chat box or raise your hand, and we'll unmute you.
Try to see the chats.
I'm looking at reactions in the chat box. So maybe I can start the discussion and just make a comment on that. It seems like there are a number of stability issues that are related to the fact that the matrix field S could degenerate inside the medium, and that seems to create issues with respect to the stability and give you log-like stability instead of linear stability. And so, so what do you think of that? And what do you think of the assumption that you made on assuming that the determinant of S should remain far from 0?
Yeah, it's true. It's a good question because it's a problem actually when you plot the determinant of S from real data, for in vivo data, for instance. You have some lines of zeros. Actually, you have some lines of degenerations. So you have two ways of dealing with this. you can say, okay, my algorithm will focus on a specific zone where the determinant of S is great. Okay, it is not 0. And so I inverse inside, and then I have an image which is great. Or what you can do is to wait, because you have several data, actually, because when you do quasi-static deformation, you will have a kind of like 10 or 20 slices of data. And so you can wait until the zone you are focusing on has no line of cancel of the determinant. So this is the two way of doing it. And the other practical way of dealing with is to like add some data. Like you will increase the size of your system with several data. So you have, instead of having just S, you have S1, S2, S3, S4, and you just simply put all this data together to a big system. It's not too difficult to do. And so you can hope that in this big system, at least, there is one data which is not degenerated where you are looking for. And so it works. But it's true that it's a very complicated theoretical issue. The only thing we can do here is to say, okay, this does not happen, and we can prove stability if it does not happen. When it happens, it's complicated. We don't know about the theoretical answer.
Right. Okay. I'm sorry, my connection is very unstable, so at times I lose the flow. But I'm again asking the audience if there are any questions, and maybe ask you for a comment also on the fact that you completely forget about what type of boundary conditions are imposed on the, it sounds quite counterintuitive in a way that you try to solve an elliptic PDE and you, in a way, dispose of the boundary conditions. So have you seen on your numerical tests that indeed what you obtain is not affected by that?
Actually, yeah, so the key is that we never solve the forward problem. So we never solve the elastic PDE because, of course, if you do this, you need the boundary condition and you need to know
Right.
it well. And so we try to forget about the forward problem completely and only see the inverse problem like a gradient inversion. Okay, and when you want to invert a gradient, you realize that you don't need the boundary value because you just have one uncertainty, one direction of unknown, which is the null space. Okay, right. And so it works the same. It means that, of course, you have this uncertainty, but it's of dimension 1. So it's not a big problem. You will have an uncertainty, and actually, this is maybe the term that I skipped. Just here. Okay. And here you see that when you want to solve your problem, you first find the null space direction. You have your operator t. Imagine that t is a gradient. It's like a gradient. You have a null space of dimension 1. So you first find this direction. You call it ZH. This is the direction of the gradient, the one who will minimize TH. Okay. And once you know this direction of the degeneration, you will solve your problem in the orthogonal of ZH. So mu h would be the solution of your problem in the orthogonal, like you would do for the gradient. You will solve it in L20. So in 2 times like this, you will have a construction of the solution, which is stable, but you don't know the part in the direction ZH. And this is the only unknown in this situation. So when you want at the end to construct a good solution, maybe you will have to add a punctual or at least a scalar knowledge, for instance, the mean of your solution or the value at one point of your solution, or I don't know, something like this. And then you will fix this constant t that you don't know, the constant, which is the equivalent of the constant value when you want to invert the gradient.
Mm-hmm.
So basically, using the boundary condition is too much to deal with an uncertainty which is only of dimension 1, actually. This is what we say, and so we accept to forget about the boundary condition. But this works because the equation is a vectorial equation. It's not like the conductivity, which is a scalar equation, and with the conductivity, you don't have enough information to do this. But with the elasticity, you have 2 equations, so it's enough. You have like a full gradient, and then you can somehow invert this full gradient.
Right, which means that you only need to use one measurement.
Yes, exactly. All these images, even the last one with the real data, the in vivo data, is an image which is made with only one displacement data. So one field U is enough to recover this this map, and so it means that it's quite practical because you can like really do a very small intervention, a small displacement, and then do the numerics and plot this image from the displacement field. You don't have to have a lot of a big collection of data to do this. You don't need waves, for instance.
Can I ask a quick question? How was, in this particular case, how was the displacement collected, measured?
So it's quite simple. You use a classic acoustic probe. So it's on a breast tumor investigation, and you simply press continuously the acoustic probe from few centimeters in the tissue. So you can do it in soft tissues, and for example, on breast or in the liver, it works well. And so you record the image on a slice of the tissue, the axis of your probe like this, and you see the image, like you see the speckle moving in the plane of imaging of the acoustic probe. Sure. It's as simple as this, and you don't need specific probe. The very classic acoustic probe in real time, like a few frames per second, is enough to measure this displacement and get the data.
Very nice, thank you.
You're welcome.
Well, I'm back again with my connection. I'm sorry, I have a few problems with connection. So if there are no further comments or questions, Laurent, many thanks again. It was a great talk. And thank you all in the audience also. We'll see you all next week for another seminar if you stay with us, and thank you again, and we wish you all a nice afternoon, morning, or evening, wherever you are in the world.
Thank you very much to everyone.